You've seen it everywhere, right? In news headlines, in that study your friend just posted, the phrase statistically significant. It just sounds so official, so final. But what does it actually mean when a finding gets that label? Is it proof? Does it mean it's important? Well, today we're going to unpack one of the most powerful and, honestly, one of the most misunderstood ideas in all of science. See, at the very heart of almost every scientific question, there's this one big dilemma. Let's say a new drug seems to lower blood pressure in a test group. Is that a real, genuine effect? Or could it just be random noise, a statistical fluke? How in the world do scientists tell the difference between a real clue and pure dumb luck? To get our heads around how scientists solve this puzzle, we're going to step away from the lab for a minute. Instead, we're going to use a super simple analogy. We're going to put a coin toss on trial. Okay, so here's the scene. Your friend grabs a coin, flips it 10 times, and it lands on heads 9 of those times. Now, your gut reaction is probably, whoa, wait a minute, something's up with that coin. It just feels wrong, right? But how would a scientist actually prove it? How do we go from just a gut feeling to a real statistical conclusion? Well, to do this, scientists use this really clever kind of reverse logic. They actually start by assuming the opposite of what they're trying to prove. This starting point is called the null hypothesis. It's basically the nothing interesting is happening here scenario. So for our coin, the null hypothesis is simply the coin is perfectly fair. Think of it like the legal principle of innocent until proven guilty. So here's the game plan. Step 1, we assume there's no effect. The coin is fair. Step 2, we look at our evidence, which is 9 heads out of 10 flips. Now, step 3 is the crucial part. We calculate the odds of getting a result that extreme if our initial assumption of a fair coin were actually true. And then step 4, if that probability turns out to be ridiculously small, well, then we have to make a decision. We have to reject our starting assumption. And let's be honest, with 9 heads out of 10, the probability of that happening just by chance is incredibly, incredibly small. It's so unlikely that we're forced to reject our fair coin theory. Our conclusion? Something other than random chance has got to be going on here. That coin is probably biased. But that brings up a huge question, doesn't it? I mean, our feeling about the coin being unlikely was just intuition. Science needs a hard and fast rule. So what's the official cutoff? How small does a probability need to be before scientists can officially call it too unlikely? And here it is. P is less than 0.05. This little formula right here is arguably the most famous and maybe infamous threshold in all of science. What it means is that the probability, the p-value, of getting your result just by random chance has to be less than 5%. That's the line in the sand. Now, this line in the sand, it has a formal name. It's called the level of significance, or alpha. And just by convention, pretty much everyone in science has agreed to set alpha at 0.05. So if the probability of your result happening by chance is less than 5 in 100, boom, you get to call it significant. But, and this is a really big but, think about what this means. We're not dealing with absolute certainty here. We're dealing with probability. And anytime you make a decision based on odds, there's always a chance, even a small one, that you could be wrong. And in statistics, this opens the door for 2 very specific kinds of mistakes. Let's break these down. A type 1 error is a false alarm. This is when we reject the null hypothesis. We say, hey, there's an effect, when actually it was just a random fluke. Think of it like convicting an innocent person. It's a huge deal because it could lead to approving a drug that doesn't actually work. Then you have a type 2 error. This is a miss. It's when a real effect was actually there, but our study just wasn't sensitive enough to detect it. This is like letting a guilty person walk free. A potential cure might get abandoned because we missed it. And this is where it all clicks together. That alpha level of 0.05 isn't just some random number. It is the probability of making a type 1 error. So when scientists agree to use that threshold, what they're really saying is we are knowingly accepting a 5% risk of a false alarm, a 5% chance of publishing a significant result that was actually just a coincidence. So how do we avoid that other kind of error, missing a real discovery? Well, the answer to that is something called statistical power. The best way to think about it is like the power of a telescope. It's your study's ability to actually see a real effect if it's truly there. A study with low power is like trying to spot a distant planet through a blurry, cheap telescope. You're probably going to miss it. So how do you boost your study's power? What's the best way to get a sharper telescope? The number one way, by far, is to increase your sample size. More data, more people in your study. It helps you separate the real signal from all the random background noise. It's kind of like turning down the static on a radio. The more you reduce it, the clearer the music comes through. Okay, and this brings us to what is maybe the single biggest, most important misconception that we have to clear up. I'm just going to read this quote directly. Statistically significant results do not demonstrate that the research hypothesis is correct. Let that sink in for a second. Getting a p-value less than 0.05 doesn't prove anything. All it tells you is that your data would be unlikely if there was no effect. The result could still be a 5% false alarm. Or hey, the entire experiment could have been designed poorly from the start.
So, if a significant result doesn't mean it's proven, and it doesn't even tell us if the effect is important or big, then what are we supposed to do? What else do we need to know? Clearly, that little p-value can't be the end of the story. We're going to need a few more tools in our belt.
A much better, more complete approach is to use a full toolkit. The p-value, which is part of something called null hypothesis significance testing, or NHST, it just asks a simple yes-no question. Is there likely an effect here? But we also need to know the effect size, which asks a totally different question. Okay, fine, but how big is the effect? And we also need confidence intervals, which tell us, and how precise is our measurement of that effect anyway? Look, relying only on a p-value is like a detective showing up to a crime scene, finding one single fingerprint and declaring case closed. I mean, yeah, the fingerprint is a vital clue, but it's just the start of the investigation, not the end of it. To build a real convincing case, you need way more evidence than that. So here it is. This is your new toolkit for evaluating claims. The next time you see a headline screaming about a significant new finding, don't stop there. Ask yourself, okay, but how large was the effect? Was it big enough to actually matter in the real world? How precise was their estimate? And maybe most importantly, was the study itself even designed well in the first place? Is this evidence I can even trust? Because at the end of the day, statistically significant isn't the final verdict. It's just the opening argument in a trial. It's a sign that says, hey, there's some evidence over here that might be worth a closer look. So now that you're a much better juror of that evidence, the real question is, what's the first claim you're going to re-examine?